Good morning, dear friends. Today we are going to discuss the topic Atropisomerism. Atropisomerism, the word is a Greek word. It is a Greek word meaning without turning. Meaning without turning. Before going deep into the Atropisomerism, let us in detail see the chirality in biphenyl compounds or biaryl compounds. The best example for biaryl compound is biphenyl compound. See, let us take this molecule, the first molecule. It is an example for the biphenyl molecule. The bond through which we do the rotation, is called pivotal bond. Okay, or some of you may pronounce as pivotal bond. Okay, the rotation takes place. Okay, this is unsubstituted biphenyl compound. It is unstable. Strong steric repulsion between the ortho hydrogens are there. Whereas when you rotate it, the top benzene ring remains as it is, and when you rotate this molecule through a pivotal bond, the benzene ring which is down here will be turned, and this is this way. They are actually 90-degree angles to each other. So this is the most stable conformation. To avoid one ring rotates 44 degree. It rotates 44 degree. Okay, not perpendicular, sorry. It is a 44 degree rotation so that there is no steric hindrance between these ortho hydrogen. Okay, so the unsubstituted biphenyl rings can be rotated around a pivotal bond. Equilibrium torsion angle, that is angle between planes, the two phenyl rings. Okay, angle between the two phenyl rings is actually 44. The angle between this hydrogen, this benzene ring and this benzene ring, the angle is only 44 degree. It is a 44 degree rotation. Torsional barriers are actually 6.0 kilojoules per mole. Okay, at 0 degree centigrade, and it will become 6.5 kilojoules per mole at 90 degrees centigrade. Okay, this is unstable because there is a lot of steric hindrance between these ortho hydrogens, and this is highly stable because it is rotated. The benzene ring which is down here having a 44 degrees to each other. They are 44 angle to each other. Okay. In substituted biphenyls, the torsional angle is up to 90 degree. In a substituted biphenyl rings. For example, let us consider this molecule here. Okay, when you see this molecule, A is not equal to B and C is not equal to D. A can be equal to C, B can be equal to D. When you rotate X and X dash are the mirror images. Okay, you rotated this molecule. So what happens when you rotate it? This ring, the down, the benzene ring, this group remains the same, and only this group, this complete benzene ring is turned. So you have B and A. They are non-superimposable mirror images of each other. So these type of biphenyl systems are chiral molecule without any chiral centers. They are chiral because of the because of the chiral axis. Okay, X can be converted into X dash by rotating the upper ring. This upper ring we have to rotate into 180 degrees about a pivotal bond. The axis passing through the pivotal bond is called, the axis that is passing through the pivotal bond through which you are doing, this is called chiral axis. Okay. So the chirality of the biphenyl system is not because there are 4 different groups, but because of the chirality chiral axis, not because of the center of chirality. Okay, for example, x and x dash are interconvertible by rotation and they show optical activity. We can restrict the rotation about a pivotal bond by substituting or increasing the ortho substituents. If you can increase, if these groups can become very bulky, you can really arrest their rotation. You can control their rotation around a pivotal bond. Okay, the stereoisomers which exist as separate chemical species because of restricted rotation about a single bond are called atropisomers. I said X, I said this x and x dash, x can be converted into x dash. Okay, they form a stereoisomers, enantiomers. But x we can stop by becoming x dash by increasing these the bulky groups here, by placing a bulky groups at the ortho substitution. Okay, then what happens, we cannot rotate them all. So that stereoisomers which exist as a separate chemical species because of the restricted rotation around a single bond are called atropisomers, and the phenomenon is called atropisomerism. Okay, now what are the different criteria for atropisomerism? What are the different criteria for atropisomerism? We will see here. The first criteria for neither ring must have a vertical plane of symmetry, but means both the rings should not, both rings should not have a vertical plane of symmetry. Okay, so for example, you take here. Okay. This is B, sorry, here A, B, B. Then again here you have A, B, C. They do not show atropisomerism because here the groups are different. But if you consider some more examples like suppose if you take here substitution is A, B, A, B, here A, and another group is present here, and here it is another B is there. A, C, B, B, D, A, B, B. Okay. These four, they show atropisomerism. Atropisomerism. Okay. The substitution, and this is the first criteria, they should not have a vertical plane of symmetry. Okay, then another one is the substitution about the ortho position must be sufficiently large so that rotation around a pivotal bond can be restricted. I have mentioned to you that the substitution at an ortho position, these are ortho positions. This ortho position substitution should be sufficiently large so that we can arrest the rotation around the pivotal bond can be restricted. Rotation can be restricted. So for example, you have some ortho groups substitution. If you put some bulky groups like if you place here acid group and here nitro group, and again you have a nitro group here, again if you have an acid group here, you can arrest the rotation. You can arrest the rotation because of the bulky groups that are present here. Maybe for example, if you have another molecule such as OH, OH, OH or methyl group, it can be a methyl group, it can be CH3 group, it can be OH group, and this also can be OH group. So these are some molecules which you can, because of the bulky groups that are present at the ortho positions, you are restricting the rotation. Okay. Now configuration of atropisomerism. Another important topic what we need to discuss is configuration of atropisomerism. For example. Okay. Like enantiomers which are chiral centers. Okay, there are enantiomers which have a chiral centers and we give them a relative configuration. We will assign them a configuration R and S. R and S. Same way R and S. So atropisomerism also have R and S. Not only enantiomers but even atropisomers. Atropisomers also have R and S configuration. Since they are optically active due to chiral axis, they are written as RA and SA. RA and SA. So we will see, like enantiomers, when we assign them R and S configurations based on the priority, same way atropisomers also are assigned R and S configuration. Since they are optically active compounds, we will note them as RA and SA. Now let us see RA and SA. To give them that configuration RA and SA, there are some important rules. First one is view the molecule from end along the chiral axis. You have to view the molecule. View the molecule from one end along the chiral axis. Around the chiral axis. Second one is label the group at ortho position. You have to label the groups. You have to label the groups at ortho position. At ortho positions as 1, 2, 3 and 4 based on the priority. Ortho group on proximal aryl ring. Ortho group on a proximal. So there is different rings that are proximal ring and distal ring as 1 and 2 and distal ring as 3 and 4. We will see what is this proximal ring and distal ring when we come. Make Newman projection formula. Third one is Newman projection formula. And the fourth one is draw an arrow clockwise. Draw the arrow as clockwise or anti-clockwise. So, as we have CIP rules to assign configuration for the enantiomers as R and S, same way we also have some rules to assign configuration for the atropisomerism. Since atropisomers are optically active due to the chiral axis, they are named as RA and SA. There are four conditions. You have to view the molecule from one end along the chiral axis, and you have to label the groups at ortho position as 1, 2, 3 and 4. For that proximal rings you will name it as 1 and 2. Distal rings you will name it as a 3 and 4. Newman projection formula you have to write. Then you have to draw an arrow like clockwise and anti-clockwise depending upon the direction and the priority of groups that are occupying. Okay, so first for example, let us consider an example. RR66 dash dinitro 22 dash diphenolic acid. Phenolic acid. Okay, so let us see this, how we are going to do. Okay, now you can make out this ring is rotated 44 degree. So you can make out this. Now what happens is suppose you are viewing from this direction. You are viewing from this direction. Imagine. Okay, you are suppose you imagine one eye is there. Okay, you are viewing from this direction. Then this ring is called proximal ring. The ring closer to the viewer is called proximal ring, and the ring away from the viewer is called distal ring. Okay, so you know first point is proximal ring, and then proximal ring groups. First of all, if you take these groups here, nitro group is there, 6,6 dinitro, 2,2 diphenolic acid, isn't it? Okay, now what happens? You have to assay. Now the first priority for the ring is, this is 1 and this is 2, sorry, 2, and same way here it is 3 and here it is 4. Here it is 4. Okay, now you draw the Norman projection formula. You leave it all the groups, just draw. You are looking from here. Okay, you people are looking from here. When you look at from here, what happens here is first the one nitro group is above. They both are actually 44 degree to each other. You just imagine. you put a palm on the first proximal ring and perpendicularly you put another palm on the distal ring. Then you can see that if your small finger and the thumb are, if your small finger and thumb are nitro group and COH is your thumb, what happens? They both are actually on the this line 1, 2, and 3 and 4 is one is below the plane and one is above the plane, above the plane. So you write below the plane 3, above the plane 4. Now you draw. Now you draw. So what happens here? It is an anti-clockwise direction. You draw it as SA. You draw it as a SA. Now this same compound you can also view from downwards direction. You view from this direction. Okay, there is one eye here. Okay, one eye is there. Okay, you view from here. Now what happens? COH view from down. COH is above the plane and NO2 is below the plane. Instead of 1 and 2, now it will be 3 and 4. Here it will be 3. Here it will be 4. 1 is above the plane. 1 is below the plane. See, 1 and 2. Now when you draw also what happens? We are drawing as an anti-clockwise direction. So it is called SA. It is called SA. Okay. So these are the two ways in which you can draw. Now another example also we will see, then you will be able to understand. Stereochemistry you can understand only through examples. Suppose there is one molecule. Okay. Now here it is a NO2. Here it is COOH. You have here again OMe, methoxy group. Here you have again above the plane hydrogen. Again here you have NO2 group. NO2 group. Now view this molecule. Okay. View this molecule from this direction. Okay, you are viewing this molecule from this direction. When you view this molecule, what happens? Before that, so it becomes a proximal ring. It is a proximal ring and this is a distal ring. Now, proximal ring will have 1 and 2. Proximal ring will have 1 and 2. So, this will be the 1 and this is the 2. This is the first one and this is the second one. Same way here 3 and 4. This will be the third one and this will be the fourth one. Now when you view from here, what happens? 3 and 4 on opposite side. Okay. So 1 is above the plane and 2, 3 and 4. Now you take, what happens? It is in clockwise direction, RA. RA. So this is the one way of assigning configuration for the atropisomers. Atropisomers. Now you have again another one is, an important topic is P and M nomenclature. P, M nomenclature of atropisomers. All the steps are same as the previous one. As we assigned, there we have discussed about the different criteria. Okay, configuration, when we are assigning the configuration, we have discussed some criteria how to assign a configuration for the atropisomerism, and there are some rules are there assigning it as R, A and SA. So all the rules remains the same, but here arrow is not. Now according to the priority of the groups, you are drawing an arrow. Suppose 1 2 3 is there, you are drawing an arrow 1 2 3, 1 2 2 3. So now when you assign PM and nomenclature, you have to directly see 1 2 3. There is no 2, there is no 2. Okay, so 1 2 3, when you draw arrow, if it is a clockwise, you call it as a P. Clockwise path P, that is plus. Okay, anti-clockwise means you call it as a M, that is minus. That is a minus. For example, you just see one important molecule you have here is okay. This means your 44-degree, this angle is there. That's why I am thickening this part. Okay. This is the, sorry. This is a 44 angle, you have rotation. So it is a little thick part here. Okay. Now what happens here? There are different groups are there. One is NO2 and another one is COOH. You have another group is here as OME, and again another group is there above the plane of the ring, that is hydrogen. Now you are viewing the molecule from here. Okay, you are viewing the molecule from here. Okay, so what happens? This is the proximal ring, this is the distal ring. Proximal ring will have, again one more group is here, sorry. Proximal group, this is the first position, this is the second position. Distal ring, this is the third ring, this is the fourth ring. So when you view this, you can really understand 1 and 2. One is below the plane of the paper. One is below the plane of the paper. So 1 here, and you have again 2, 3 this side and 4 this side. 3 when you look, it comes to your right side, 4th it will come to your left hand side. Okay, so what happens now? Here is not 1 2 3. You cannot draw this way. Not 1 2 2 3, but it is a PM nomenclature. You are drawing directly 1 2 3. So 1 2, I mean you cannot draw an arrow from, let me see. You cannot draw an arrow 1 2 3. Okay, this is wrong. This is wrong. You cannot assign atropisomerism for this way. Okay, you cannot. You cannot this, but you can only assign nomenclature of PM directly by drawing to 1 2 3. So 1 2 3 is actually, it is a clock, it is an anti-clockwise direction, so it is assigned as a M. It is assigned as a M. Okay.